Welcome back to the Deep Dive. Today, we are taking a fascinating, and I mean a really detailed journey, stripping away all the layers of abstraction. We're going straight to the core mechanics of modern computing. We're talking about decoding the x86 architecture. This is the engine that's running most of the world's computers.
It absolutely is. And our sources today, they're basically a definitive guide to x86 systems. We're looking at everything from memory structure to the most fundamental assembly instructions.
So what's our mission with this one?
Our mission is to give you a foundational, jargon-free look at what's really happening at the lowest level when your program does something simple. Something like calling a function. We're kind of unlocking the secret language of the CPU.
Mapping out how data and control flow are managed, because when you write code in, say, C or Python, you're relying on all these abstractions.
Right.
But here, we're looking at the meticulous, almost legalistic rules that govern that whole process. The stack, the calling convention, all of it.
Think of this deep dive as building a mental blueprint of the CPU's workspace. We're going to show you the surprising logic behind function execution, why data is stored the way it is, and how the processor always knows where it is and where it needs to go next.
So where do we start?
We have to start with speed. Let's talk about the CPU's fastest storage areas, the registers.
Okay, let's unpack that. If the CPU is the brain, then the registers are its high-speed scratch pads.
Exactly. They're the fastest variables you can possibly use because accessing main memory, that takes much longer.
And we're focused on modern x86 processors, the 80x86 family.
Yeah.
Our sources say if you were debugging, maybe with GDB, the info registers command would be your window into this.
It's your window into its soul, really. Now, modern CPUs have a lot of registers, but we need to focus on the original 4 primary 32-bit general-purpose registers, or GPRs.
Okay.
They are EAX, ECX, EDX, and EBX. They are key to understanding the calling convention.
And these act as the main variables while instructions are executing.
Yeah.
EAX is the accumulator, right? Often for results, and crucially, a function's return value.
Correct. And ECX is the counter, often for loops. EBX is data, and EBX is the base.
That's a lot of variables in play.
It is, and they're multi-purpose, which brings us to one of the first major rules of the function calling convention. Because EAX, ECX, and EDX are used so often for temporary calculations. The x86 architecture has a very specific rule. If the function caller needs the current values in those registers to survive a function call, it's the caller's job to save them.
Wait. The function that starts the call has to save the values.
Right.
Why is it asymmetrical like that? Why not just make the function being called save them?
That's a great question. It's a performance optimization, really. It's a rule of trust. If the Cali, the function being called, had to save everything, every single time, it would add so much unnecessary overhead.
I see.
So by putting the burden on the caller, which is the only one who knows which of its own variables are actually important, you save cycles. The Cali can then just freely use EAX, ECX, and EDX as its own scratchpad.
That immediately reframes the whole thing. It's not just a collection of variables. It's a system of shared, optimized responsibility.
Yeah, precisely.
That's fascinating. But okay, before we get deeper into how these registers move data, we have to talk about something really fundamental, something that determines how every multi-byte variable is stored. Endianness.
Right. Endianness is one of those things that seems really abstract until you're staring at raw memory bytes. It just defines the order that the bytes of, say, a 32-bit integer are stored in memory. You've got 2 types, big endian and little endian.
Okay, walk us through it. If I have a big number, how does big endian store it?
Think of it like you write a number on paper from left to right. In big endian systems, the most significant byte, the biggest part of the number, is stored at the smallest or lowest memory address.
So you read it just like you write it.
Exactly.
And little endian, which is what x86 uses, it flips that script.
It flips it completely. Little endian stores the least significant byte at the smallest memory address. So if you wrote out a hex number and then looked at how it was stored byte by byte in memory, you'd see the bytes physically reversed.
The small end of the number comes first. Why? Why did Intel choose that? Big endian seems so much more intuitive for us humans.
Well, our sources point to a couple of practical reasons. The main one is that little endian makes it simpler and faster for the CPU to access data of different sizes from the same address.
How so?
For example, to read a 16-bit word from a 32-bit integer, you just read the first 2 bytes at the lowest address. Done. With big endian, you'd have to calculate an offset. It's really an architectural choice that optimizes for the machine, not for the human eye.
A great illustration of optimizing for performance. Okay, so we have the GPRs for data and endianness for how it's laid out. Now, what about the registers that manage flow? The pointers.
These are the backbone of program control. They don't store data values, they store 32-bit addresses, locations, and memory. And we need to focus on the big three for program state: ESP, EBP, and EIP.
Let's start with the two that manage the stack pointer and the base pointer, ESP and EBP.
Right. ESP, the stack pointer, is the most dynamic one. It always points directly to the very top of the stack, the memory address of the last thing that was added.
And the stack is always growing and shrinking, so ESP is always moving.
Constantly moving.
So if ESP is always moving, why do we need EBP, the base pointer? Why not just use offsets from ESP to find everything?
That's the critical question, and it gets to the heart of the function frame. EBP acts as a stable, fixed reference point for the entire time a function is running. If you used ESP to find local variables or parameters, the address would change every time you pushed or popped something.
Oh.
By copying the value of ESP into EBP right at the start of a function, you lock in the base address for that function's territory.
So EBP is the anchor. It gives you a reliable way to access everything, like local variables and parameters, using predictable offsets no matter what ESP is doing.
Precisely. The caller's parameters will be at positive offsets from EBP, and the callie's local variables will be at negative offsets. It's the key to maintaining structure.
Okay, now for the executive register, the one telling the CPU what to do next. EIP, the instruction pointer.
EIP is, you could argue, the most vital for understanding execution flow. It points to the memory location of the current instruction the processor is reading.
The physical location of the next operation.
Yes, and our sources really highlight why this is so important for debugging. If you can manipulate EIP, you directly change the flow of the entire program.
It's the literal flow control mechanism.
Yeah.
Okay, so the ESP, EBP, and EIP trinity is basically the management team.
Absolutely. The GPRs handle the data, and these three pointers manage the state, memory, and flow. And now that we have the who and the where, let's look at the how, the language of the CPU.
Assembly, the verbs of the CPU. And what's interesting is they're actually pretty intuitive mnemonics, even though they're so low level.
They are. The most foundational instruction is move. It's simple. Move a value from a source to a destination, like mov at esp. We use that constantly to set up that stable EBP anchor we just talked about.
And then you have the two instructions that really define the stack's whole existence.
Yeah.
Push and pop.
These are critical. Push places a 4-byte operand onto the top of the stack. But here's the conceptual hurdle we mentioned. Because the x86 stack grows downward in memory, a push instruction doesn't increase the address. It actually decrements ESP by 4 before it places the data at that new lower memory location.
So high addresses are the bottom of the stack, low addresses are the top. That trips everyone up when they first learn this. It feels completely backward.
It is, but it's a deliberate choice, and pop is the mirror image. It removes a 4-byte element from the top, moves it to a register, and then it increments ESP by 4, moving the pointer back up towards a higher address.
Cleaning up the stack space. And this whole push and pop dance is what higher level instructions like call and read rely on.
Exactly. Call secretly pushes the current EIP, the return address, onto the stack and then jumps. Read does the reverse. It pops that stored address off the stack and back into EIP so the program resumes where it left off. But this whole process relies on a very strict social contract.
The function calling convention.
The convention, yes.
Okay, let's dive into that. This is where everything registers, pointers, instructions, it all comes together. When a function is called, all the local variables, parameters, the return address, everything gets pushed onto the stack.
And it requires this strict 2-part dance to ensure everything works. It dictates the responsibilities of the caller, the function starting the jump, and the callie, the one being executed.
Let's start with the caller rules. What's the setup process before control gets handed over?
The caller has 3 main jobs. First, what we already mentioned, register preservation. If the caller needs the values in EAX, ECX, or EDX later, it has to save them on the stack first, protect its own data.
Check. Now, what about the data being passed, the parameters?
Second job, parameter passing. The caller pushes all the parameters the callie needs onto the stack, and here's the aha moment. They are pushed in inverted order. The last parameter is pushed first.
This seems so weird. Why? Why that inverted order?
It's all about accommodating a variable number of arguments. Because they're pushed in reverse, the first parameter is always stored closest to the return address at a predictable spot.
Ah. So the callie, which might not know how many optional parameters came after the first one, can always find that first required argument.
It can always find it using a consistent offset from EBP. It's an incredibly elegant solution for language features like variadic functions.
That turns a weird quirk into a really essential mechanism.
It does. And once all the parameters are on the stack, the third step is handled by the call instruction itself, which pushes the return address right on top. That's the last thing the caller does before jumping.
Okay, so the stack now has, from bottom to top, any saved registers, the parameters in reverse order, and the return address. Now we're in the Kali. What are its first moves?
The Kali's main job is to set up its own stable context, its stack frame. And its first two actions are known as the function prologue.
The prologue.
Step 1. It has to save the caller's EBP value by pushing it onto the stack. This is like leaving a breadcrumb, so when it's done, it can restore the EBP of the function that called it.
Storing the old anchor so we can get back to it.
Exactly. Step 2. It executes move esp. This takes the current stack pointer and locks it in as the new EBP. The new function's stable base is now set.
That makes the EBP-AP relationship crystal clear. ESP keeps working, but EBP is our reference for the current function.
And then the Kali allocates its local variables, usually by just subtracting from ESP. And those variables are now accessed using negative offsets from EBP.
So let me just visualize this. Once the Kali has its stack frame set up, EBP is the reference point.
Yeah.
Positive offsets from EBP get me to the parameters the caller passed in.
Yep.
And negative offsets from EBP get me to the local variables that the Kali just allocated.
That is the perfect visualization. Parameters are at positive offsets, locals are at negative offsets. And this discipline structure ensures that when the Kali is finished, it knows exactly how to clean up and where to go back.
This all seems incredibly robust. Everything on the stack is relative to that EBP anchor.
It is the essence of control flow. And it leads directly to the final, most critical rule, the exit strategy.
This is where it gets really interesting then. If the whole point of this system is to hand control back smoothly, what's the one single piece of data that's most critical?
It's that return address, which is used by the RIN instruction. Because of the strict, non-negotiable setup of the stack frame, the architecture guarantees something vital.
Which is?
The return address of the caller is always, always guaranteed to be at the memory address EBP plus 4.
EBP plus 4 bytes. That single memory location is the guaranteed exit route. The anchor, EBP, gives us immediate access to the instruction pointer we need to jump back.
It's the crux of control flow reliability. The Kali just has to run its epilogue, the cleanup restore, the old EBP, and then execute ret. That instruction pops the value at EBP plus 4 off the stack, throws it into ELT, and boom, execution resumes right where the caller left off.
That's an incredible insight. Okay, let's synthesize the key takeaways for you before we wrap up this deep dive.
First, x86 architecture is little-endian, storing the least significant byte first to optimize for the machine. Second, the ESPED EP Trinity are your core managers for the stack and program flow.
And third, the stack demands that parameters are pushed in inverted order. It's that clever trick that allows for variable arguments. The biggest takeaway for me is that the CPU isn't chaotic at all. It follows this incredibly disciplined, almost bureaucratic plan.
Absolutely. The calling convention is like a handshake agreement that every piece of code has to follow, ensuring data is safe and execution is predictable.
And while that structure is powerful, knowing that the most critical piece of control, that return address, is stored in a fixed, predictable location, EBP plus 4, well, that introduces a single point of focus, doesn't it? The whole system relies on the integrity of that one address.
A single predictable spot in memory holds the key to the program's future.
Exactly. So what potential challenges or maybe vulnerabilities might arise if that specific address were intentionally manipulated before the result instruction is executed? Something to mull over until our next deep dive.
Always something more to discover once you look under the hood.
That's it for this deep dive. We hope you feel a little more informed about the meticulous engine running your world. We'll talk to you next time.